Welcome to The Explainer. This is where we dive into complex topics and break them down by going straight to the original source material.
Okay, so let's get right into it. This is a fantastic story about a revolutionary AI architecture, a really subtle limitation that went unnoticed for years, and then a shockingly simple fix that changed everything.
Now, to really get the hero of our story, we first have to understand the problem it was designed to solve. So imagine you're dealing with really complex data, right? Stuff like a social network, or maybe the structure of a molecule. You can represent this as a graph. Well, the early models for this, called graph neural networks, had a pretty basic approach. A node would just kinda average together the information from all its neighbors. And that's the key problem. Just averaging everything means you're going to miss the most important signals. I mean, think about your own social network, right? Some friends have a huge influence on you, others not so much. The big question in the field became, how do we teach a model to focus on what actually matters?
And then, in 2017, the Graph Attention Network, or GAT, showed up, and it seemed like the perfect answer. GAT brought this idea of attention into the world of graphs, and the promise was huge. Now, every node could learn to weigh the importance of its neighbors all on its own.
So, how did this thing work its magic? Well, to put it simply, for any node you pick, it would look at each of its neighbors and basically calculate an attention score, a number that says, how important are you to me? Then it just creates an updated picture of itself based on a weighted sum. The whole idea was that it could learn a totally unique importance weight for every single connection in the graph.
And I mean, this was a massive breakthrough. GANs were powerful. They were efficient, and they just shot up in popularity. They quickly became one of the most trusted, most used GNNs out there, crushing the state-of-the-art records on all sorts of standard tests.
But then things got interesting. In 2021, a new paper came out from researchers at Technion and Carnegie Mellon, and they asked a really sharp, really important question. Was this attention mechanism really as dynamic as everyone thought it was?
And what they found was kind of a bombshell. It turns out GAT doesn't actually compute that flexible dynamic attention everyone assumed it did. Nope, it computes something they called static attention. And what that means is the model basically creates a single global ranking of important nodes. And that ranking is the same for every single node in the graph.
This analogy they use just illustrates the problem perfectly. Static attention is like a food critic who publishes one top 10 restaurants list for the whole city. Everybody gets the same recommendation, doesn't matter what your personal taste is, your budget, where you live, nothing. GAT was basically creating a global these nodes are important list, and every other node just had to go along with it.
But here's the absolute kicker. The flaw wasn't in the big idea of graph attention. It was in a tiny, subtle detail in the math. And the fix? It was almost unbelievably simple.
Okay, so don't get too hung up on the formulas here. The big idea is all about the order of operations. In the original GAT, the math was set up in a way that two key steps kind of collapsed into one less powerful step. The new version, GAT-v2, just swaps the order. By applying one function before the other, they unlocked a way more expressive, way more powerful model.
And that one tiny change, that simple swap, allowed GAT-v2 to do what everyone thought the original was doing all along: compute true dynamic attention.
So let's go back to our restaurant analogy. Dynamic attention isn't that food critic with a single list. It's like having a personal concierge. It asks you, the individual node, hey, what are you looking for? And then it gives you a recommendation tailored specifically to you. Each node could finally actually decide for itself which of its neighbors were the most relevant.
Okay, so this all sounds great on paper, but how do you actually prove that this little tweak makes a real difference? Well, the researchers were clever. They created a special test problem called dictionary lookup, which was designed to be basically impossible to solve if your model could only do static attention.
And the results, I mean, just look at this. They are absolutely stunning. The original GAT, even with a single attention head, which you can think of as like one channel for paying attention, it completely fails. It can't learn the pattern. Give it 8 heads, and okay, it can memorize the training examples, but it can't generalize at all. In GAT v2, it nails it. 100% accuracy with just a single head.
Now, when you actually visualize what the original GAT is paying attention to, you see the problem clear as day. All of these query nodes, Q0 through Q9, they are all laser-focused on the same wrong answer, key node K8. They've all agreed that K8 is the most important node, even though it's wrong for almost all of them.
But now, look at GAT v2's attention map. It's a perfect diagonal line. Every single query node dynamically finds its own correct answer. That's dynamic attention in action. It's not just better, it perfectly solves the puzzle.
And you might be thinking, okay, that's a neat synthetic test, but does this actually matter in the real world? And the answer is a resounding yes. The researchers tested GAT v2 on 12 different real-world tasks, stuff like predicting chemical properties or analyzing code, and the results were always the same. GAT v2 consistently and significantly beat the original.
So what's the big picture here? What should you take away from all this? It's about so much more than just one algorithm. It's this powerful reminder that even our most popular, most celebrated models can have these hidden flaws. It shows that a tiny little change in how you write the code can lead to a massive change in what the model can actually do. And it proves that we have to keep critically examining our tools if we want to make real progress.
And what's really cool is how the original creator of GAT, Pedar Velikovic, reacted. He totally embraced the finding. He basically said, look, GAT was great for the kinds of problems we had back then, but today's problems are harder, and they demand more powerful and expressive models, exactly like GAT v2.
And that just leaves us with this one final, really provocative thought. In this incredibly fast-moving world of AI, where it feels like a new breakthrough model drops every single week, what other fundamental assumptions are we getting wrong? What other hidden flaws are just sitting there waiting for someone to find them?